Okay, so let's wait for a couple of minutes to see if we have our audience also ready on board.
Mm-hmm. We should be able to see their
Yep, I think
viewers
so.
in
So let me
StreamYard
see.
itself.
Yep, I'm just trying to, perhaps maybe see the chat box and okay. At the moment, I think it's only okay. Okay, I think we have some audience
Okay,
ready.
we have some first chatters.
Yeah.
Hello, welcome.
Hi, everyone. Good evening. So perhaps we wait for a couple of minutes. Meanwhile, perhaps, Takwin, if you like, maybe you put up the PowerPoint. I will also go on this mode. So we have our faces also on the screen. So
I'm sharing it right now.
Okay. Very well. Good. So I think perhaps we start and gradually I think people will join us. Hi, everyone. This is Amin Tully, and you're on my YouTube channel, Water Edu Hub. Today, we have this live webinar about machine learning for rainfall-runoff modeling. We will go through fundamentals, a case study, and model comparisons. And today, I have my colleague, Dr. Tokwin Chang, also helping me. So two of us, we are going to cover these topics, and the algorithms that we have are going to be ANN, random forest, XGBoost, and our benchmark model, which is GR4J. So let's get started. I think perhaps we go to the next slide. Yep. I was thinking that perhaps for those who are new to our channel, I just give a bit of intro. So this channel started a year ago. I'm as the founder of this channel, and here my mission is basically decoding complex water and climate challenges with practical insights. And then the next one, perhaps here I also need to highlight that our website is coming up very soon, and there we are going to have some resources available for both the students, researchers, and practitioners. Stay tuned. I will update when the website is ready. So the next, please. So here I have a quick intro about myself. I hold bachelor's, master's, and PhD in civil engineering, and I have had 20 years of work experience in academia, at consulting firms, and also with government bodies across 4 different countries. But it's good to also highlight that my main focus throughout all these years have been hydrological and hydraulic modeling. And during my PhD, I did a kind of focused study on hydrological modeling and forecasting with machine learning tools, which is the topic of today. I pass to you, Takwin, to introduce yourself as well.
Hello, everyone. Welcome to the stream. My name is Dr. Takwin Chang. So I did my degree in electrical and computer systems engineering, and for my PhD, I was supervised by Prof. Amin himself, and we were specializing in hydrological modeling and forecasting using machine learning as well. And after my PhD, I worked 3 years in data science for several tech firms. And beyond that, currently I'm in my current job as a AI systems integrator for the last year and a half. And
Thanks.
welcome, bring back to you.
Yeah. Thanks, Lakmin. Thank you very much. And of course, it has been my privilege to work with you throughout all these years. We are getting almost close to 10 years, I guess, since the
Yes,
time
10
we
years of
started to work together.
collaborations.
Yeah.
Yeah.
Okay. The scope of today's webinar, the first thing that I want to highlight is that today we are not focused on any kind of programming or coding. The whole idea today is to provide some fundamental, or let's say introductory session about machine learning applications in rainfall-runoff modeling. But we have designed this webinar for both types of audiences, those who are totally fresh to this topic, and also those who have some background and want to learn more and also get familiar with some challenges related to basically this topic. So the first thing that I want to highlight is that I think perhaps we jumped, we need to go back perhaps a few slides. I think we just jumped forward a lot.
Yeah,
Can you go back? Yeah, no worries.
So we'll go back to the scope. All right.
To the scope, please.
Oh,
yeah.
I
think we are just jumped
slide
a lot.
has messed up. Yeah.
Yep. Okay.
There we go.
Yeah, so the outline of today's presentation is going to be basically going through some fundamentals related to machine learning and also the processes of developing them. Of course, at first, I'm going to answer a very important question, that why in the first place we need all these basically ML algorithms as an option for ourselves. And then, of course, the development stages of that. Then we will introduce the algorithms that we are going to use and also our benchmark model. Then we have a case study. Then we will go through the results and model comparison and lots of interesting discussions about the challenges that we have had in that process and also interesting findings of that. And then we will have our takeaway session and finally the QA one. So if you are interested to have any question, please put it in the chat box. Towards the end of the session, we will get back to all questions as much as we can. So please move on to the next one, please. Yep. So one thing that I like to highlight as housekeeping and also for the engagement one is that our session is going to be recorded, and immediately after the session will be uploaded in the channel for those who want to watch it again or share it. And also be noted that in the middle of sessions, we will have some pause perhaps in order to answer a couple of questions. Okay, so the first thing that we wanted to highlight is this question, that why machine learning for rainfall runoff modeling is basically needed. So let's go through the hydrological processes and see what is the reason of that. So when we look at the rainfall runoff process, in general, we are having several challenges. Let's go through them one by one. First of all, the process involves lots of components like precipitation, evapotranspiration, the interaction with soil, the interaction with atmosphere, and so on. And all of them add to the nonlinearity of this process. So it's a very nonlinear scenario for us. And then when we look at the catchment as a whole, we have this spatiotemporal heterogeneity, meaning that in different corner of the catchment, means different space, we have inconsistent information of hydrological data. It means that they are not consistent, they are changing in space, and of course also in time. And that's another level of complexity. The other problem that we have when we simulate the rainfall runoff process is equiphenolity, meaning that by having different pathways between the parameters, we may get totally similar results. And that will be problematic for us, especially when we are calibrating a model. The next one is going to be the non-stationarity. We know that the processes are not stagnant. They are not stationary. They are changing in time through several processes like climate shifts, land use changes, or even sometimes natural disasters like wildlife burns that can change the hydrology of the catchment. And of course, our human intervention when we do modifications in the catchment by putting some regulations on, let's say, rivers. And the last one, of course, is data scarcity. We know that several parameters related to the hydrological processes that we are talking about are either not measurable easily, or we don't have enough resources sometimes to basically cover that data collection. So these are the challenges. Now let's move to a very important point. We have different types of models in order to simulate the rainfall runoff process. From left to right, we have physically based models, conceptual models, and empirical models. And by looking at them, it is quite clear that from left to right, what is happening is the process representation by these models are going to be totally different. So on the left, we have physically based models that are very transparent, and they basically have a very good representation of all hydrological processes. And when we move towards the empirical one, that transparency get lost, and practically we don't have much representation of physical processes. The other important point that I want to highlight is about the fact that the number of hydrological variables involved in these type of models are also different. When you go to the physically based model, you need to have lots of parameters involved, like evapotranspiration, rainfall, runoff, soil properties, and so on. But when we go towards the empirical ones, practically we play with very limited number of variables, and that's a bonus. That's a good point. For example, most of the time only rainfall and runoff. And the last point is that the data hunger also is very different. When we go to the physically based model, the model can be developed with a small amount of high quality data. But when we go towards the empirical ones, because they are data-driven approaches, they are highly dependent on very lengthy, basically, data. Of course, algorithm to algorithm, that data hunger will be different. And we are going to discuss that point. So now let's move on. The question that here we have is that, okay, why machine learning? Here, the fact is, when we are working with machine learning, there are several capabilities in them that actually match very nicely with all those challenges that we have in rainfall runoff modeling process that I mentioned. So the first one is all the ML algorithms are known to be very good in capturing nonlinear relationships. Secondly, they are also very good in working with large data sets, and they are very helpful when we are dealing with hydrological cases that we have very long time series available most of the time. The next one that is going to be important is that when we are working with the hydrological processes, certain algorithms are capable basically to somehow capture the temporal dependencies. And we know that in hydrological modeling, time series analysis is very important, and those ML algorithms have this capability for us. The next one is the fact that no a priori assumptions also are needed, means that you don't need to have lots of background of the physical processes of the catchment. As long as you have data from it, you can proceed with model development, and that's a bonus. And the last one is the fact that we have lots of modern algorithms that can handle very interesting things like collinearity, or, for example, moving from one catchment to another catchment because of the transfer learning that they have, and also being adaptive. That's what Takwin and I have worked a lot on it in the past with some algorithms, and also the fact that they are very good tools for real-time modeling. So with all these important points, ML is a good option. At this stage, we can consider it as a good option for rainfall runoff modeling. So let's move on. The next part of our talk, we are going to go through the process of developing a rainfall runoff model by machine learning algorithms. So we want to know, what is the workflow? What are the steps that we need to go through? So let's move on. The first thing is, of course, data preprocessing. Data is the most important component of ML model because it's a data-driven algorithm, and data quality is very important. So practically, we need to handle the data and work with it a lot. So the first thing that I want to cover is the data requirement. So generally, the first thing that we need to highlight is the fact that, as I mentioned earlier, these type of algorithms can work with minimum number of hydrological variables. And I would say that minimum for us is only rainfall and runoff. But occasionally, in some cases, we may need to consider temperature as well. One of our experiences in the past was working on a Scandinavian catchment, for example, and there the snow melt is a very important factor in the hydrology of the catchment. And because of that, you cannot just rely on rainfall and runoff to develop a model. And their temperature time series can be a factor helping us to somehow resemble the process of a snow melt in that catchment. So that's something that sometimes we may need to consider. The next point is about the length of the data. And as you see, it's just a general guide, not like a written rule, to say that generally we are expecting having like 3 to 5 years at least to start with, and the more is the better. But of course, that is going to be different from one algorithm to another, because some ML algorithms can work even with let's say 1 or 2 years, means they can still give very good results, but some maybe not. So that is depending on the type of the algorithm that we use. And lastly, the difference between continuous and event-based modeling. When we work with the event-based modeling, it's very important to also have certain number of high quality events. I would say 15 to 20 at least, and they should be basically diverse as much as possible. Events that are very different with each other to provide enough information to model during the calibration. The next one, I want to go through some of the processes that we do or some of the tasks that we do in order to prepare our data before using it in our model. The first is, of course, quality check. So 2 tasks we generally do. The first one is checking for the missing values. If they are random missing values, maybe 1-2 points here and there, we have options of infilling them. There are several methods for that, and we can adopt it. But if it is like a big chunk of data set and you think that perhaps infilling may be uncertain and you cannot rely on that, for example, let's say a couple of months are missing in, let's say, one of the stations, perhaps the best approach is to cut that part of data set from all time series. Means that if you have, let's say, 5 rainfall stations and 1 flow, and one of the rainfall stations misses, let's say, 6 months of data, and you don't have the option of infilling that, then what you need to do is just removing that 6 months from all data sets to make sure that they are consistent in length and you can basically fit them into your model. Another point is anomaly detection. Make sure you visually check your data. There are also statistical methods for that. If you see some anomalies, for example, a very large peak suddenly appears in your flow time series, please verify that. Make sure that there is a kind of historical event or flood being recorded somewhere. And if not, you need to explore whether that's a mistake in your data. So make sure what you use is reasonable because our models are data driven. So if you feed them with wrong data, they are going to give you also wrong answers. So that will affect the training. The next component is normalization. That's a common practice to normalize the data. Of course, certain algorithms may need it significantly, maybe some of them maybe not. So during this process, what we do, we transfer our data into a certain domain. For example, by this example that you see on the screen, the formula, it's a kind of linear transformation that you can bring your data into a domain of, let's say, 0 to 1, and you apply that for all your data sets. This is basically helping the mathematical functions in machine learning algorithms to work better. Also note that in some papers in the past, for certain algorithms, like, for example, ANN, some of the mathematical functions may not work with 0 perfectly. So there have been like published work saying that it is better to stay away from 0, and perhaps the domain that you choose is like 0.1 to 1 or 0.1 to 0.9. So there are papers for that. Make sure when you use an algorithm, do a bit of literature review about this type of needs for your algorithm. The next one, the third, is temporal splitting. Means that whatever data set you have, you need to divide it into 3 pieces. training, validation, and the testing. The first two are going to be used for calibrating the model. And what we mean here is also called basically kind of training validation process in order to adjust the structure and also the model parameters. The percentages that I have put here are just indicative. In general, we are expecting to have the major chunk of the data for calibrating side, and we reserve around 15% of that for testing. We have also some best practices here. For example, it is advised that it is good to use the latest part of the data for training, because if your catchment has gone through some changes, you calibrate your model based on the latest information. The second one says that in case you are having like a splitting like what I've shown here, make sure statistically they are similar to each other. And that means that when you look at parameters like standard deviation or mean, we have relatively close relationship between them. It's not like you train something and then test it on something totally different. So that's also a very important point. And the last one says that you can basically go for a cross-validation process as well. Just talking about the example that is on the screen, let's say if I have a 60% data set for training and 20 for validation, I may split my training into 3 pieces, 3 of 20. And then what I'm going to do is swapping them. So it means each time I choose 3 out of 4 for training and leave 1 for validation. So I mix the validation and training data set and swap them. And then I look at the average performance when I want to adjust my model parameters to get the best result. Once done, I go to the testing. So testing is always the unseen data set, the one that we basically only go to really test our model and see the final performance of it. Okay, let's move on. The most challenging task, I would say, in rainfall-runoff modeling with machine learning algorithms is input selection, because these are the parameters that you choose to tell your model the relationships between your inputs and the outputs. And here we have relatively diverse options available. So when I say rainfall, that means you may have rainfall from different rainfall gauges. And beside that, you also may have different antecedents of data set from every single rainfall gauge, which I'm going to explain very soon. Similarly, you can have antecedents of runoff or some upstream runoff stations available in order to just look at them and basically use it. For example, imagine you have a very large catchment and you have like 3 flow stations in it. You use the most downstream part, the part of it as the one that you want to simulate, and then maybe 1 or 2 of the upstream runoff stations are going to inform the downstream one. Temperature, I think I mentioned about it, if needed, only in perhaps snow melt cases in very cold climates. So now let's talk about the output. Output is generally runoff or water level. And most of the time we are interested to having it at present time. In case if it is a forecasting case, we may want to have it in the future time steps. For example, a couple of hours later, or sometimes even a day later, depending on the time series that we are working with. Next one. I want to show what I mean by input, basically. So imagine we have this catchment with a couple of rainfall stations. So perhaps one of my first question is, which stations or stations should I choose for my model? And that's the part that is very challenging, and we are going to cover it very soon. The next question that I want to have is that, let's say if I choose station number 4 as an example, which antecedent of it is going to work for me? So that means if I shift them in time, I'm maybe, let's see whether the slide comes up. I think it has, okay, it's there. So here we have this antecedents. What I mean by antecedent is basically the lag time. It is because we know that in reality, there is a lag between rainfall and runoff because of the travel time or the catchment response time. So in order to resemble that, what we do in inputs preparation, basically we may have the lags of it. So that means imagine the first column in the left is the original time series of the data. I may want to have like one time step lag, 2 time step lag, and so on of it, and consider them as potential inputs to the model. So that's the part that we are going to discuss very soon, how we assess that. Okay, the next one in the input selection is some of the famous methods that are available. Perhaps one of the most important one is cross-correlation analysis. And in this process, what we do basically is calculating the correlation coefficient between our potential inputs and our desired outputs. Let's say rainfall as input and runoff as output. And then what we do, we present our results in form of some visualization. For example, we can have it as a correlation heat map, color coded, to see what are the stations or what are the lags that basically have the best correlation with our desired output, which is runoff. The left one shows cross-correlogram. This specific example on the screen is from one of the past studies that we have done that shows the correlation between runoff and the antecedent of one of the rainfall stations up to 10 time step lag. And that means basically, and that I think the time step in that study was 10 minutes. So for example, 10 time step lag means 100 minutes of lag. And as you can see, these diagrams generally will give you a kind of bell shape in general. And we are interested in the peak or some points around it, because these are basically the antecedents that potentially are highly correlated with our output, and we may want to consider them as input. The next one is mutual information. That's also a very important method. We know that some of the potential inputs that we have in mind may have some mutual information. In other words, easy way to explain that, they are saying the same story to the model. And we are not actually interested in that, because if, let's say, I have two inputs that are highly actually having like high mutual information, I may not want to consider both of them because they are telling the same story. And I'm actually getting my model complex for nothing. So here, mutual information helps us to exclude any kind of input that is not going to tell us anything new. And the next one is what I did during my PhD. It's actually a mix of the past two methods, the mutual information and cross-correlation method known as MICA. Later, I think during Takwin's PhD also, he did some work on this method and expanded it for event-based application and also continuous application for rainfall runoff modeling. And there are published works on that. If anyone interested, we can share it definitely. And the last one, the last method that I'm going to cover here is the wrapper method. In this method, basically, what we do is a kind of trial and error. So it means that we have some options. Let's say I have 10 potential inputs. Then I look into all possible combinations of choosing inputs from there. For example, combinations of choosing 2 out of 10, 3 out of 10, 4 out of 10, and so on. And you know that basically we do that by this binomial coefficient calculation. So we can do that, and we will end up with lots of options. And we run our model for the calibration data set only with all these possible scenarios of inputs to see which combination of inputs give us the best answer. Of course, it's very tedious. And because of that, it is very common to use some sort of optimization methods to that, meaning that instead of just covering everything, you can have a kind of optimized version of it, something like a smart trial and error that can go through, and if it sees that basically some of the combinations may not work, it will avoid repeating them in the next iterations. The next one, by the way, Takwin, do you want to add anything to that, the wrapper method?
This is a bit of a lesser method that I've used to before. Usually we go with the input selection methods that were more commonly used for input selection through like mutual information and correlation methods. The wrapper tends to be a little bit more complex to use because you tend to need to run the model in its entirety for each input, for each combination of feature input. So it takes a lot of time, it takes a lot of computational power to run it.
That's
So
right.
it is a method, but it's a method that is reserved for really complicated data sets.
That's right. My personal experience with that also wasn't that good. I remember I used GA as the optimizer, and you're right. I needed to leave my laptop for, let's say, 2 days to run all possible scenarios, and it was like a very big set of inputs available as potential inputs, and basically that didn't work well for me, and I decided to stop that. It is not worth really trying, except if it is really needed in your case. Okay, let's move on. Okay, so now we go to the training and validation part. So once you have your training data set, basically what we do is just feeding the data into our model. And when I say feeding, we are providing both inputs and our desired outputs, because we need to provide both X and Y for the model to find the associations between them. So as you can see, for example, here I show two columns. Let's say I have only one input and I have only one output. So I should provide both input and output as a pair to my model. So I let it learn the associations between these two. So that's the first step. Next one, it goes to the model, and the model also has some parameters. So that model parameter adjustment is going to happen. So beside the inputs, we will have some model parameters in the ML that is going to play their role and create some output for us. Perhaps maybe you click on it, talking to go to the next one. So it shows the adjusting, and after that, having the simulated output. And then what we do, we look into the objective function. And normally here we are using something like, for example, least square error or this type of error functions. And our target generally is minimizing it as much as possible. So if that objective is not satisfied, we need to go back. If it is satisfied, we end the process. So it's a kind of loop mechanism. We circle around until we get what we want from it. And once it is done, our training is completed, we can go to the next stage, which is the validation. So let's go to the next. So in the validation part, I think we lost one. Yeah, I think the validation part here, basically what we want to do is doing a bit of fine tuning and make sure that we can basically make our model even better. So here, after the training, we run our model for the validation. Again, we do the same process. We compare it with the objective function to see whether by adjusting or further adjustment of the model parameter or the architecture of it, we can basically improve it or not. So the same thing is happening here. We are checking with the objective function. If it is now better, we stop. If not, we need to continue the process until we get the best answer. And once that one is achieved, basically we are going to fix our model. We are not allowed to change anything. And then we move to the testing part. So that's the end of a calibration process basically for us. So the next slide is going to be the testing part, of course, the last stage. So here what we are going to do is, as I said, with a fixed set of parameter architecture, we just move to the testing. We run our model for the unseen data set. And straight away, we go to look into the performance of that. And here the best practice says, start with the visual inspection, have hydrograph, Scatterplots in order to see how your model performs. And then also we need to look into multiple performance metrics. Don't rely on one, and make sure you are looking into different aspects of your hydrograph, like overall shape, pics of it, the volumes, and also the timing, especially if you are working for example, a kind of flood warning system or something. The timing becomes quite important. I have also some other videos on the channel available. If you are interested to know more about performance metrics, please watch them. It has a tutorial as well. So these two videos are like episode 1 and 2 of the same topic. Okay, let's move on. Now we are at the stage that we want to introduce our 3 machine learning algorithms of today's discussion: ANN, random forest, and XGBoost. So the first thing that I want to go through here is answering one question: why we decided to proceed with these 3 algorithms. So let's go to the reason of that. In general, I would categorize the ML into these 5 categories. Our target for today, as I mentioned earlier, was to start with something that is relatively easy to understand, easy to develop, and also it is nicely covered in literature with the application of rainfall-runoff modeling. There are, of course, sophisticated versions. For example, even on the neural networks, we have DNN, deep neural network, or we have these recursive neural networks, or LSTM, which I'm sure you have heard of it. It's a very complex model. But again, because we wanted to touch on something fundamental, something easy to digest for today, and perhaps in the future, we can cover more on that. And the other items under 3, 4, and 5 are specifically designed algorithms for certain purposes. And yeah, you may not see them frequently everywhere. They are generally the one that we may want to use them in certain applications. For example, our work, I think Takwin and I worked on Safin and also Denfis algorithm on the number 4 neurophase systems. And our target at that time was developing adaptive models. And because of that, these type of models were useful for us. And they're, of course, a bit complex to discuss. So we proceed with 3. 1 comes from neural network family, and 2 come from the tree-based methods. They are quite strong. They have been used a lot in rainfall-runoff modeling, and today we are going to discuss them in a case study as well. So let's move on. I start with the neural network. Neural network is basically a very, I would say, interesting resemblance of our brain. It is a very old mathematical work. I think the very early work of neural network has happened back in 1930s or 40s as a mathematical work. But of course, it waited until computer science reached to the level to use it in real application. So how it works, as you can see, it's a network of neurons and links. It resembles the neurons of brain. So in general, we have 3 layers: input layer, hidden layer, and output layer. The hidden layer itself may have multiple layers, as shown here, but most of the time, even 1 layer may work for us. And then each layer has also certain number of neurons that are shown as circles. The connection between them, we call them link, and generally there is a weight associated to that we are going to discuss very soon. So let's move on. So if I look into the connection between input layer and hidden layer, what is happening is this. So we have inputs coming in. The link will multiply them to a certain weight. So there are like specific weights associated to each link. And then it goes to a kind of computational unit that add up these values, and it will add a bias number to that. This bias is like fine-tuning parameter. The model will work on it during the training and change it frequently. And then it goes to the activation function. It does a calculation and produce an output for us. And this single output from that single neuron will be sent to the output layer. And the output neurons there are sitting, receiving multiple calculated outputs from different neurons. They just add them up, they integrate them, okay? And that is the final output that we get. So there are 2 set of model parameters. The model parameters, weights and biases, are going to be automatically basically adjusted during the training, but there are hyperparameters that are going to be adjusted by us as the user. For example, the architecture of the choice. that we have, like how many neurons I put, how many layers I put in the hidden layer. These are our options, and we can play with them. What type of activation function I want to use mathematically, or what is the layering rate, how fast or how slow the layering is going to happen, and the epoch number that tells us the iterations, for example. So that's our choice of parameters, hyperparameters. The next one is the random forest, and it is basically a very interesting method. Perhaps to make it simple to explain, imagine you have basically a kind of single predictors sitting and working independently, and then at the end all these decision makers will produce a kind of estimation of your runoff, and you just average them. So how it works, in the first step, we have bootstrap sampling. So the original data set goes there, and it will be broken down into subsets, basically. And then random feature selection happens. Then the trees are going to be developed, and they are happening simultaneously and independently. They're growing, going deep and deep, and some branches introduced to that. And at the end, we have the aggregation. So it means the final prediction is averaging whatever predicted values are there. If we go to the next slide, we have a visual representation of that. So I've just show it as a kind of simple way. Imagine we have like 3 trees, and at the end of the process, each tree has an estimation of the runoff based on the input that it has received. So the first one says 36, the second one says 41, and the last one, let's say, says 38. And the average of that will be our final value. So how that process happens, it depends on, again, some model parameters and some hyperparameters that we adjust. Takmin, do you want to add to that?
Yeah, so the beauty of this model is that because we're averaging throughout all of the trees, right? A typical run, we could have quite a few number of trees, can be up to 50, can be up to 100. And by averaging all these trees, what's amazing about this model is that it doesn't allow any kind of like strong biases or overfitting of data. Everyone gets an equal weight of, like sort of an equal weight of the decision that is made. And so this kind of model is very easy to train. It's very robust. It's not easy to, it usually runs straight out of the box. It's very simple to understand. And it's later we can go through a bit furthermore, but there is also something we can interpret from within the model parameters itself.
Exactly. Yeah. Thanks a lot. So yeah, let's move to the next one, which is the XGBoost. So as we mentioned earlier, that's also part of the tree family, but there is something interesting. So if RF was like, I just resemble it in this way. Imagine it was like a panel of independent decision makers. When we come to XGBoost, we have a panel of specialist trees that are designed in a way to correct the other decision. So means that if the first one make a decision, let's say tree 1 come up with a number, the second one actually look into the error of that estimation and try to fix it, try to make it better, and then pass it to the next one. And this sequence of improving is happening one by one. So that can become like very fast. It's a very interesting process that can improve the performance instead of having like independent guesses that may not be very good at first. So this is why XGBoost perhaps is considered as one of the very highly performing models in ML family. The other point that we want to also highlight, perhaps maybe we go to the next one. Yes, this is the point that people may say, okay, what makes it extreme? The fact is a very interesting mechanism that is built in, and that's actually hidden in the second part of this equation that you see as the objective function that tries to penalize any kind of trees with too many leaves. In other words, it has a mechanism to stop itself from growing unnecessary trees in the algorithm and keep the model as parsimonious as possible. And because of that, it will actually avoid a famous problem that we know as overfitting. And overfitting, that I perhaps needed to mention it earlier, is one of the traps that we have during the calibration process in machine learning. During the overfitting, the algorithm is tending to memorize rather than learning, and that's something that we don't want. And an indication of that is you see a very good performance in training, but your performance during validation is not good, or even in testing is become even worse. So generally we don't want to have that. So the whole idea is to design our algorithm in a way that we don't go through the overfitting problem. So, Takwin, I think you want to perhaps maybe highlight the fact that these type of algorithms generally are somehow immune from overfitting. Am I right? Please add to that if you like.
So not specifically for XGBoost, not as much as the previous random forest.
Random forest,
where
yeah.
Yes, so random forest is a little bit more robust towards overfitting because you're
Yep,
averaging against many multiple trees. But
that's
this
right.
one,
Yeah.
you're overcoming the problem of generalization from random forest, where
Yep,
instead of taking all equal weights from all the different trees and averaging them, you're sort of going expert by expert, tree by
yep,
tree, to help update the value. And
that's right.
by doing this, you can also uh we can
Fall in the
learn like
trap of
really
memorizing. Yeah,
uh specific pieces of information that would be important. For instance, when we are doing rainfall runoff modeling, like
yep,
there are certain times when you have flooding events. In random forest, the problem is they would generalize it too much. They would average it out, and you wouldn't get that kind of like recalling of this kind of rainfall flooding events. But in XGBoost, we do not have that kind of problem, and so that's what it's trying to build upon the problems
yep.
of random forest.
That's right. Yeah. Thanks a lot for that additional point. So let's move on. The next one that we are going to talk about is our benchmark model. We have this conceptual hydrological model as benchmark. Uh, Perhaps in the next slide, what you can see is the mechanism of it. It's a very simplistic model. It's a French model developed in 2003. It's very well known in Europe, and it's a lumped model, means that it resembles the whole catchment as one hydrological unit. And what we have is that here basically we have 4 parameters, and these 4 parameters are dedicated to like different aspects of the work. You can see that some of it, for example, look into the routing process, some of it look into the soil moisture stuff. So the process here is that it receives rain and evapotranspiration, and depending on which one is dominant, it basically proceeds to the soil moisture, whether we are losing water or whether we have the potential of runoff generation. And then a very interesting mechanism in that is that when we go to the runoff generation stage, we have this split of 90%, 10%. So this proportion is fixed in the model, and for the fast and the slow processes. Uh, we have dedicated parameters for each of them. And if you look at the slow one, that also has a kind of hydrograph generation and also routing process in it. And once these two pathways go independently, at the end, they will also go through a kind of groundwater exchange, whether they are giving or getting water from the groundwater. And then at the end, these two branches will be added together as the final estimated stream flow. So the strength of this model is its simplicity. It's a very parsimonious, basically, algorithm. Perhaps if you click on it, Takwin, we can have it written also. It's physically motivated, but it's a conceptual, means that still some of the parameters in it may not have real physical meaning or something that is measurable in the catchment. So they are like parameters. We play with them. They are resembling something physically meaningful, but not a real physical parameters. Equifinality problem is there. The model is originally designed for daily time steps only, and it's a lumped model, means that it's not covering the spatial variability in the catchment. So we purposely use this one, and the reason is if our ML models can present at least equal to this or better than that on the very challenging scenarios, we have basically ticked the box. So this is like a benchmark. So we need to meet basically that basic performance from ML, basically to call it something reasonably acceptable. So let's move on. Now we have our case study. I need to mention something. Honestly, today we really didn't want to present or cherry pick something nice and show that machine learning is performing super well in that catchment. No, the idea is exactly opposite. We purposely decided to go through a very difficult and challenging scenario that any modeler that works with machine learning may face. It's a very rare scenario, but we purposely put our case study for that. So what we are going to do today is very interesting. First of all, we are adjusting ourselves based on an available study that is done by JR4J. And that available study works only on 6 years of data. And split that data set, perhaps if you click on it, Takwin, that will be shown. So we have almost 6 years of data, and rainfall, we have 11 gauges, and runoff, we have considered one basically runoff. I think there is a typo there. It's not at the outlet. Basically, the flow station, as you can see, is that red dot in the catchment. And the reason is that it's a coastal, the outlet of it is a coastal outlet. And we know that generally flow measurement near the coastal lines are not good because it will be affected by tidal effects. And generally for rainfall runoff modeling or flood forecasting purposes, we need to go inland. And we have chosen this station, which is inland, and that reduced the size of the catchment. So the challenges we have is the data. It's a short data set. The second challenge is that we are dealing with lots of rain gauges, and we need to decide which are the ones that we want to consider as the input. So let's move on to the next slide. We have done a bit of statistical analysis on it. So here you can see that I start with the flow. If you look at the flow values, something challenging again for us is the very diverse range of the data that we have. So if you look at the mean value of it during these 6 years is 4.2, and the max of it is 13,000. So you see how big is the difference here. And I think the witness of that is also the standard deviation and also the skewness. You see that the data is really skewed, and it has a very large standard deviation of close to 700 cubic meter per second. So that makes the modeling very challenging. Rainfall stations, I think nothing is special about them. They are relatively almost similar. Of course, there are ups and downs in them in the recorded rain. And the reason of it is because the catchment is a very large one. Part of it is mountainy, part of it is floodplain. So they have different hydrological behaviors. So the rain is different in them. To the next slide, you can see the hydrographs and also hydrographs of the available data. Nothing special here I want to highlight, except the fact that if you just look at the plots, even by eye checking, you can see that there is some lags between rain and runoff. Runoff is sitting the top, and the rainfalls are at the bottom. You see some of them are actually having like a delay, and that tells us something that perhaps because of the scale of the catchment, which is a very big one, we may have some lags in it. The next one is very interesting. I think that's also another very challenging point. I wanted to compare the training and the testing data. Here, what we did was, because of the short data that we had, the 6 years, we just followed the way that the temporal split was done by other researchers for the GR4J. So in that study, they split the data half-half. They use half for calibration and half for testing. We also do the same. So we are using the first half for training and validation and reserve the remaining half for the testing. So that's not something traditional in machine learning, but we do it here to put ourselves in challenge. The second challenge here is that if you look at the calibration and testing data sets, the statistics of that, you will notice that the testing data set is relatively higher in almost all the statistics. The mean is higher, the max is higher, median, standard deviation, and so on. And also the skewness of the data is also very interesting. I purposely calculated all the percentiles up to P99, and you can see that up to P95, we are in the scale of few hundred cubic meter. And then suddenly when we go to P99, the numbers are going to like 1,000. But in reality, if you look at the max values on the top of the table, you see that they are like in the scale of 11 and 13,000. So that means the percentage of that high flows in our time series is very, very, very a small percentage of data set. And that's not good for machine learning because it's a data-driven algorithm. If we provide very little amount of high flow data points, our model is somehow biased toward the low flow values. And the first thing that we are expecting is that most probably this algorithm is not going to perform well in those very high flows. Okay? And we want to just assess it. That's the first thing. The second thing is, if you look at the max of calibration and testing, you see there is relatively around like 20-25% difference. The testing is higher. And that means our model is going to extrapolate. And we know that that's not the strength of machine learning. The machine learning algorithms are generally not good in extrapolation. They always can perform very well up to the limits that they have been trained for. So these are the challenges that we have purposely decided to have to see what is the performance, how the models are going to work here compared to the benchmark algorithm. So let's move on. We have done an input selection process. We did the correlation heat map first. If you look, I just want you to have a look on the first column. As you can see, the light color stations of rain, perhaps they are the one that we may not want to choose. And the one that are more blue, perhaps are the potential highly correlated ones, but not necessarily all of them are going to be the good ones. I think based on what I see, rainfall station number 1 and rainfall station number 8 are the ones that are having very low correlation, and most probably they are not going to be selected during the process. Not by us, by the process, basically. The next slide looks into the cross-correlogram. Remember, we mentioned that they are going to be bell shape, and here we have it. Almost all rainfall stations show around 1 day lag time to the runoff. In other words, RT-1 from any station potentially is one of the good ones. And of course, around it, we have RT, means with no lag, and T-2 and T-3 also relatively okay. But when we go further to T-5, 6, you see that it declines and potentially they are not going to be something valuable for the model. But we don't know. We need to go through the process because that will be decided by the algorithm, the Mika algorithm that we are going to use. Okay, next one. So here we have a very interesting input variable also. Takwin, do you want to talk about it, the moving average rainfall?
Sure. So when it comes to machine learning, occasionally the features, the input features that are available typically may not be sufficient for these ML models to capture some of the physical properties that is happening in real life. Because when we talk about rainfall runoff modeling, there's a lot of complicated processes. And part of it is that it's hard to capture some of it through only rainfall data, right? So when we add certain features, we call this part feature engineering. And one of the features that we engineer here is the moving average rainfall, which essentially you're taking the average of a few rainfalls time steps, and you're averaging them and taking the new value, and you're doing this at every time step. So in this case, there's a window size of 2, so you're taking 2 values, averaging them into a new column, and you're moving down the time step. And so this is this is basically prolonging 2 days of data into one, essentially mimicking something that is a bit long-standing. For instance, like soil moisture, it could be some water storage property, and by doing this, we can sort of mimic that kind of physical behavior. And the other input feature that we are adding here is the lag discharge, because we can simulate our data based on whatever happened in the past. So one day before the actual simulated discharge, we can take the previous day's discharge and inform the present day's discharge on what kind of relationships there are. And so we've included these 2 input features as part of the model. Back to you.
Thank you. Yeah, thanks a lot. Perhaps we go to the next one. So after doing the Mika process, we found basically this set of 5 inputs. So QT minus 1 means the first antecedent of discharge, plus 3 rainfall. The one that is shown as R3 moving average 2 is the one that Takwin just explained. It's on the basically the 3rd rainfall station, moving average of the 2 of the antecedents. And then we have from the 3rd, the 4th, and the 10th station. So I think you may be interested to know why these stations are chosen. So if we look at the map, what is interesting is that these stations are located in different parts of the catchment. So Takwin, please maybe click on it. So as you can see, just automatically without our instruction, the algorithm have chosen stations from different corners of catchment, because that combination is more informative. It covers like more diverse rainfall information to the catchment, contributing to that flow measurement point. So that's the interesting part of it, that if you look at the selected input, sometimes you see some interesting physical meaning of that as well. The other point that I want to highlight, if you click to the next, is comparing that with the basically heat map that we have. What is interesting for us is that if you look our input number 10, Takwin, I think if I'm not wrong, what I see is 0.39 as the correlation coefficient of that. And basically, that one is not the highest. We have a couple of other rainfall stations with higher values, but that one is basically is like 0.39, what has been chosen. And that's the interesting part of it, that tells us the fact that not necessarily anything with the highest correlation coefficient, meaning that it should be chosen for us. It could be something else that also may be chosen because of perhaps maybe lesser mutual information or other facts. So that's the interesting part that I wanted to highlight. Let's move on. Okay, so Takwin did also an interesting sensitivity analysis here. There is also a notion, or maybe understanding, or I call it misunderstanding among some of the users, to say that the more inputs we use, the better will be the outcome. So here we want to show you that if we look at the progressive increase of number of inputs, starting, let's say, from 3 all the way to 8, the reason that we stopped at 5 is basically reasonable. If you look at the NSE value for the 3 models that we had, you can see that from 3 to 5, we have a nice increasing trend. And then when we move to the 6, basically it gets stuck. there is no much of improvement in ANN or maybe even in XGBoost. Perhaps random forest, if you see, it gets a bit better. But in order to make the judgment whether I need to go to the 6 or not, I also look into other parameters. The next slide shows the p-bias value. P-bias is the one that checks the overall volumetric estimation performance of the model. And here, if you look at the comparison between 5 and 6, you can see that the ANN start to get worse. The green color bar increases when we move from 5 to 6. And that means that from 5 onwards, some of our algorithms are starting to have more errors in the volumetric estimation, although the NSE shows slightly better, but we should not make that judgment based on it. So that's the reason we stop at 5. And our message here is that the answer is no, not necessarily increasing the number of inputs give us better results. So that's an evidence of that. So let's move on to the next one. Takwin, I pass it to you to go through some model parameters.
Yep, so over here we see some of the, we're going to go through each of the 3 model parameters, just as a very simplified view, because all of these models have hyperparameters that we can tune to sort of improve the model performance and to control the amount of memorization it does to prevent overfitting, right? So the few that are important here are probably the learning rate, the type of activation function, which is usually ReLU, although we have several other types, but these are the most common configurations that are quite reliable, like epochs are the number of cycles. So we will tend to see trends of machine learning algorithms having the ability to control mainly the learning rate and the number of cycles, and just other parameters that allow us to control how it minimizes its learning curve. So this is the ANN model parameters, and for the random forest, we are using about 500 different trees to have the average value for our final predictor, and we've set the depth of 12, so each tree has sort of 12 different branches below it, and these are quite basic parameters that we use as well. And in XGBoost, here we have the learning rate is set to 0.03. The number of estimators here is the number of trees that we're using, and so there is an ensemble of 1,000 interconnected trees, and that is used to get the results that we'll show in the results section.
Good, thanks. Yeah, now let's move to the results. Let's see how these models perform. We'll start with statistics, the performance measures here. As you can see, our GR4J sits at the bottom of the table as our benchmark. The performance of it under NSE and R square is around 0.7. And when it goes to the other parameters like RMSE and MAE, you see that it's in the scale of few hundred cubic meter per second because of that huge difference between the low flows and high flows. And the p-bias is really good, 3.4. Generally, anything below 15% is considered as acceptable, reasonable. And then when we go to our ML models under all these challenging scenarios, you see that XGBoost is still slightly outperforming our GR4J in NSE and R square, as well as RMSE and MAE, but in the p-bias, it's not performing better than GR4J. The other 2 algorithms also not bad. I don't call them like bad. They are okay. Especially ANN has a very good performance, and perhaps you can see that the value of MAE in that one is perhaps one of the best, even better than GR4J, better than our benchmark model, interestingly. So that means that the absolute error is relatively good. But yeah, other scales are almost there. So we want to visually also see what is happening. So if we go to the next one, the next slide, we have the hydrographs being plotted as expected. You can see that the those high peaks in the testing data set are not performed very well. And that's the reason, because they are beyond the calibration, and also the model has been trained by a kind of biased or skewed data set. So almost all models, including our benchmark model, are not performing well when it comes to the very high peak values, the two spikes that are seen on the screen. The next one, we have the Scatterplots, and perhaps with that, we can better see the underestimated values. The underestimated values are the lines that are basically the dots that are below the 45-degree line, and anything above that is overestimation. So generally, they have performed relatively close to each other, some of them slightly better than the other. The one that is very interesting is the peak estimation. So for this time series, we have decided to consider the 95% percentile as our threshold for choosing the peaks, basically. So any peak that is above that 90% percentile, we want to look into the peak estimation performance in that. So as you can see, all the peaks that are above the red dash line have been chosen, and then we have calculated the the peak error in that, relative peak error, or RPE. And if you want to know what it is, it's basically the difference between simulated and observed peak divided by the observed peak, and then you can multiply it by 100 to make it as percentage. So here, interestingly, ANN has a slightly better peak estimation compared to the others, but the other ones like XGBoost and RF are also there. I'm comparing the line in the middle of the boxes as the median value to just make my judgment. You can see that almost all machine learning algorithms are slightly better than GR4J. Another factor for comparison here is the outliers. So those algorithms that have too many dots out of the box means that they have like outliers. They are the values that are really perform bad. And ANN in that sense is perhaps the best, because not only has a better median value, it also doesn't have any kind of outlier in the box. So that's also a good point from performance in the estimation of the peaks. So let's move on to the next one. Here, if I want to make the final call to say that, okay, what is the best model out of our machine learning algorithms, definitely we may go for XGBoost because of the overall performance and also a relatively good value in the p-bias compared to the others. But if I want to choose anyone for the peak estimation, ANN will be the winner out of them. And if I want to compare the overall performance with GR4J, I would say we have had relatively comparable performance. So although the scenarios were not in our favor, the models are still performing reasonably acceptable when it is compared with the benchmark model. So the next for us here is to go through deeper understanding of what we have here, the interpretability of the models. So we want to see what are the things that are happening inside of these algorithms when they create these values. So Takwin, I pass it to you to go through these.
All right. So the one of the important points when it comes to ML models is just to understand the processes that is happening within the model itself, right? Because often we want to know what is going on underneath it. Unlike physical models where we usually have a better understanding of the water balance mechanisms that's in play, in ML models, we sort of need to, some of these models have features in a way we can extract some understanding. So for the tree-based models, generally it would look something like this, where you have a bunch of decision trees, where this is one of the trees within the ensemble itself that it was using to decide. And you can see that its first decision of when they put the data in was to look at the moving average of the data set first, and they determine if it's less than a certain value, it would lump into a whole set of other decision trees. And if it's to the right, it would go to a different branch of the tree itself. And it goes down through the layers. And at the end of it, we will come up with some kind of estimated discharge value that it has been pre-trained on. And so because this is one of the trees, it would go to another, it would keep updating itself through the following, the rest of the ensemble of trees. And so this is for the XGBoost, and one of the good things about the tree-based algorithms is we are also able to see what are the features that contributes to the minimizing of the loss function of the algorithm. So over here, the algorithm has shown that the moving average was one of the most important features that it was used to identify or to quantify the value of the discharge. The second one would be the discharge antecedent, and then it just goes a bit lower weightage on the rainfall values. So likewise, we have the same kind of understanding from the random forest algorithm. It's also tree-based. This is one of the 100 that was used to simulate the runoff. And this is only because random forests rely on much deeper trees. This is only showing the depth up to 2, where in fact the tree does extend all the way down to 12 separate child branches. And this is, of course, only one of the 100, where it will average off with the others. It also came up with the similar feature importance in terms of rank compared to XGBoost. It found that the moving average, which is supposed to be a representation of soil moisture or water storage, performed the best. It captured the most information out of this compared and following it is the discharge antecedent, and some of the rainfalls was also a big contribution. Probably the least is the rainfall R3. And so we go on to ANN. ANN doesn't really inherently have this kind of feature where it's able to tell us what is the contributing feature that is responsible for every discharge output. But we have because of its low interpretability of ANN models, we have a method of extrinsically finding out what is happening in the inside. So we've run a bunch of, we've basically chucked a bunch of, we reran the model by changing the input data one feature at a time, and we observe how did each of this feature contribute to the model performance. And so this is not really a telltale sign of the complete picture of what the model thinks it's the most important representation, but it's more of a representation on average. So perhaps that features or that this of low flows that are more frequent would probably use Q as its most important feature, but when it comes to high flows, because it's so irregular and it's so infrequent, it might completely look different of what it considers its most useful feature here. So it kind of gives us some sort of insight, but it's not as interpretable as compared to the decision trees.
Perfect. Thanks a lot. And now we have a live demo of some of the works. So you see how the process is working. So Takmin, please share your screen on that and proceed.
Okay. I noticed we do also have a few questions. Maybe we should get to it at the end. What do you think?
Yeah, I think perhaps maybe better I compile them and perhaps towards the end we cover the questions.
Okay. All right. So let me share my screen and we'll show a short snippet of some coding for XGBoost.
Meanwhile, I also highlighted, I put a link in the comment for those who haven't registered, in case if you're interested to receive the lecture slides plus some reading material like the journal papers that we mentioned, and some other material. Just please register, provide us your email address, and we will be happy to share it after the session. As I mentioned earlier, it's not covering the codes because that's not the focus of today's webinar. We are not providing any programming codes here. Thank you.
Okay, give me a second, and there we go. Okay, so over here, we'll do a simple live demonstration of how XGBoost works in terms of like how do we model it in programming. So what I will be programming in the language that I'll be using is Python, right? It's a very common language used in a lot of data science and analytical applications. If anyone's interested, the software I'm using is VS Code, also a very popular coding software. And so what I will go through today would not be an entire coding practice, but we'll just go through a quick rundown of how the coding works and how the modeling process looks like as well. So I've already pre-typed some of the codes ready to go, just so we can start loading the libraries, some of the data. And as it runs, we'll see that, okay, we'll be working on the Clarence catchment as well. And this is the data. This is the data set that I will be using, which is also the same data set as what we just presented. It's the Clarence catchment, and we have 11 columns of rainfall data and one column of the discharge, which will be our target variable. And similarly, we'll be doing our train test data split of 50-50 here. And under feature selection, so what we'll do is we'll run the Mika 5 algorithm to find the 5 best inputs that would be used for the model. So running the algorithm has shown us that it's using these 5 inputs, which we've already shown the results for it prior during the presentation. And what we'll do is we'll separate this our data set into using the features that were selected. So now we have 4 different data sets, data frames here, which are the X-train, Y-train, X-test, and Y-test. These are the training and testing data sets. The training and testing for the input variables have 5 columns to represent the 5 features. And the Y-train and Y-test is basically our discharge that we are trying to predict. And this is just the example of the data set. So we will train our model over here. And so the model training, we'll go through step by step on how the process works. So I'll just run some initialization. And now here is where we'll define the parameters for the model. So let's say I prepare a space to define the model parameters. And over here, maybe we call it XGB params. And we'll leave it blank for now. And then subsequently, here is where we'll develop the model. So we'll start by using the model that I've already preloaded. So the model is under the XGB model that I will use the fit function. And I'm going to fit in the training data sets. So I've already have the training and the test over here. And what we will do is we will input as well the evaluation set that would be used to illustrate the learning curve, as we'll see in a short moment. So the first eval set we'll use is the training data set itself to see how the model learns from and performs for during model training, and the testing set to see how it performs on a data set that it's not trained on. And yeah, so this will be the model that we'll be using. I've not defined the model here yet. So the model is the XGBoost regressor. And I will be inputting the model parameters from here, but I'll leave it blank as of now. So what it'll do is it'll just take the default values. And once I did that, the model will fit the training data set, and I need a way to predict the outcome, predict the Y value. So I'll generate the prediction. Okay. And what we'll do is I'll feed in the testing data set. I'll feed in the testing data set so that we can get the prediction for the testing data set, and then we'll compare. So now that we have it, we'll evaluate the performance matrix between the predicted value and the Y test data frame. And what we will do is I already had prepared a matrix calculation function beforehand. And I will be comparing the observed value, which is Y test, and the predicted value, which was produced by the model. And if we give it a run, it should run on the initial values. Oh, model fits. Oh, something is wrong here. I might not have imported all of the libraries yet. Technical difficulty. I did not encounter this during the issue. Yeah,
it's okay. Yeah. So if you want, perhaps maybe we can move on to the next part. Maybe if you once you fix it. Yep.
I do have a data set. I do have a file that I've already pre-prepared.
Okay, yeah, maybe show that one. Yep. Because anyway, as we mentioned earlier today, the focus is not really programming. So
yeah,
so
the steps if I were to
important. Yep.
be able to fix this,
yep.
I basically have a mimic of the code right here as well.
Yep.
And basically, we'll run this model.
Yep.
And it will show on the default parameters that was used for the modeling. This is the result that was produced. Okay, the performance result is decent, NSE of 0.67, and this is the loss function that it plotted. So what the loss function is basically showing how the model performed during training at each time step. Okay, it's split into the training and validation loss curve. So you can see that there is about 100 rounds, 100 iterations of updating the model. And the first step of updating, usually we see the worst performance. And this curve is showing how much it learns through the different iterations over time. So the problem with this model so far is because it's using just the base parameters, which I've a summary of right here, it's using an estimator of about 100, which is 100 ensemble trees, and the learning rate is 0.3. So based on those values that it has predetermined, we can see a kind of problem here where there's quite a lot of overfitting. When we look at the training loss curve, the training RMSE goes all the way to 0, which is a problem because this just signifies that it's memorizing the training data set while having the validation testing set as not a very good result, right? You can't have the training set perform very well and your testing set perform very badly. So this is a classic example of overfitting. And also that we can see that the training basically stops around the 20 boosting round, which after that, it no longer improves the models that much. So that is also another feature of overfitting that is, we have multiple layers of overfitting. So how do we fix that? Is that first we play around with the learning rate. So if the learning rate currently is 0.3. So let's say if we go down to a learning rate of 0.1, we can see that it has basically sort of slow down the learning so it can come to a more stable point later in the iterations. Now, if we want to, the learning is all right, but typically we want to have the model with about 100 to 1,000 trees deep, and that's where it performs the best. So let's say we want to get the trees to about 500. If we run with these parameters, what we see is that it's not utilizing the full 500 trees. Within the first 30 or 40 trees, it has already basically memorized all of the data. So I would slow down my learning rate even further. Oh, sorry, I would quicken my learning rate. Oh, sorry, it's the other way around. I would slow it down further so that it has time to catch up and learn the training data. But it's still, the RMSE still approaches 0, which is still a problem of overfitting. So we need to, the model is overfitting, it's not generalizing enough. And so we need to limit its complexity of the model so that it doesn't overtrain through memorization. And one of the ways is by applying one of the regularization functions to the model. And what it does is it just reduces complexity by putting a penalty on each of the tree nodes that is basically close to 0. It's just contributing noise. And by reducing the noise, we improve its generalization. But at the same time, we introduce the max depth, a lower max depth, right? Because when we have a max depth of a higher max depth, means the tree is deeper. And so it's memorizing, it's also contributing to overtraining by overfitting. Its complexity increases. So we want to reduce the complexity, improve generalization. So we reduce the depth of the individual trees to 4. And let's see how the model performs here. So only looking at the curve for now, just excluding the metrics, we can see that, okay, the training curve has now not really approached to 0 as before. It's a little bit more stable, where the validation set has also improved in terms of its RMSE. Previously, it was about 500, and now we've improved the validation set performance slightly as well. So this is indicative of just a bit better in terms of generalization. It's not overfitting as much. Now we can see that the training stops at roughly around, well, not training stops per se, but the performance of the validation set has stopped around 200, right? Because anymore, it's not really contributing to the data set. And moreover, if we look at the training, it's just all of this additional training that it's doing is just overfitting to the training data set. So what we'll do is we'll call it quits at the 200 mark. So we will limit to just 200 trees here. And so the final parameter, the final structure of the model that we'll end up is at the 200 mark. The training curve and the validation curve looks very good. There's much less overfitting. The tendency for the training set to RMSE to go to 0 is not as bad as before, so it's not overfitting. And so this model would be considered acceptable at this stage. It has an NSC of 0.7, and the MAE has further reduced. Earlier was almost twice the MAE, and now the model is performing reasonably. And so, of course, there is a lot more tuning that we can do. In our final model, we went through some of the subsampling, a bit of randomness that we introduce into the model, and all of this contributes to the optimization of the model, that we can improve the results later on. But so far, for now, this is the conclusion for the session. And I'll pass it on to you.
Thanks. Yeah, thank you very much. Yeah, perhaps maybe we move back to the slides. So I think, yeah, this is the overfitting problem that we mentioned earlier. And here we wanted to have a kind of live demonstration that, yeah, it's a bit difficult because you are dealing with like multiple parameters. You fix one, maybe the other one become problematic. So you need to really spend some time on that. Of course, there are tools that can figure out the best combination through optimization, but again, that one also need expert feedback. You need to eventually look into it to make sure that what you get is acceptable. Okay, so we have just a few more slides to wrap up the session, and then perhaps we can move to the QA. Takwin, could you please put it on? Yeah, okay. I think what we want. No worries. Yeah.
Give me a moment to look back the previous PowerPoint
I think we are now
slide.
at the, yeah, at after that demo slide. We start from that point.
Let me share my screen here.
Yep.
Okay.
Good. So,
and we'll return to.
Yep, exactly. After the demo.
Sorry, hold on.
No worries. It's okay. So let's move on to the takeaways, basically. Just quickly have some important takeaways. Next slide, basically, we cover a couple of important facts. The first one is that, as you saw, despite the challenges that we had and also the limitations in the data, ML models achieved relatively acceptable performance. My key message here to everyone is that we are not looking at ML algorithms as a replacement for physical or conceptual hydrological models. They are going to be our tools available for alternate scenarios if application allows us. So that's the key message. They are like kind of complement to the system, not a replacement. So the next one is going to talk about the fact that basically almost all models, including the benchmark, didn't perform well in peak estimation, and that was the data issue, because the data that we had for calibration and the testing was skewed. It was mainly towards or biased around the low flows rather than high flows, and no wonder that we get bad performance. The next one talks about the fact that all these algorithms learn from data. So the size of training data set matters, and it influences our performance in the testing part. And because of that, the diversity is very important. We need to have a good mix and balanced mix of low flows and high flows to train our model. And the next one is about the fact that the limitation that we had in the data, the choice of algorithm can still help us to have a better performance. And in order to show you that, yes, more sophisticated algorithms, even under such challenging scenario, may perform a bit better, we go to the next slide to show you one of our past works with SAFIN, which is a neurofuzzy algorithm, one of those adaptive models. you can see that its NSE can go up to 0.821. The p-bias is much better than ANN, XGBoost, and Random Forest. And when it comes to peak estimation, it is much, much better than GR4J and also other algorithms. So the reason of it is because its nature is adaptive, means that when it hits the first high peak flow that it hasn't seen, immediately it will adjust itself. After the first bad error that it's going to have, it will revise itself in order to perform better in the next one. So it's a kind of gradual improvement in its model. And because of that, perhaps maybe it loses the first peak, but when it goes to the second high peak, it performs very well. And because of it, you see that the overall performance becomes better. Next slide is about basically the fact that when should we use the ML? I would say that when the catchment has a long clean historical record, because data matters. If you don't have it, ML perhaps is not a good choice, except if you work with certain type of algorithms. The next one is the fact that the catchment processes are quite complex and heterogeneous in some of the cases. And if you're dealing with some catchments like that, maybe ML is a good choice, especially the cases that we have poor understanding of the physics of the catchment. Then ML is a good choice because it's a data-driven, and that lack of knowledge about the catchment doesn't matter. The next one is talking about the case that if your catchment is dealing with heterogeneous inputs, there are algorithms that can use them directly without honestly handling them or spending too much time on selecting specific ones. A very good example of it is LSTM, for example. The next is about the fact that when prediction accuracy matters more than the physical explanation, then perhaps ML could be a good option. A very good example of it is forecasting. When you are dealing with a warning system and you are interested to have accurate, quick predictions of multiple time steps ahead, perhaps maybe machine learning is one of the good options there. And the next one is going to be about the things that you need to be cautious about. Today, we talked about the fact that extrapolation beyond the training data is not the strength of machine learning. So be aware of it. That's why we say that the more historical data you provide to your model, you are somehow guaranteed that perhaps that issue is not happening. But you know that. Still, we cannot guarantee 100% that it's safe because it's a kind of a stochastic scenario. Still, any big event that hasn't been seen in the historical data can happen. And we know that the model is not performing. And the next one is about the data quality. I think we touched about it earlier, that the quality of data should be high and also the amount of it, enough to train the model. The next is the fact that overfitting is a really serious issue. Takvin just demonstrated that in XGBoost as an example, that very easily by using some default parameters, perhaps you get into that trap. You overfit your model, and that means that its predictability when it goes to the testing data set is not going to be good. The next one is about the input selection. Go for the fact that basically input selection deserves real care. It's very challenging, and spend time on it because that matters. That inform the performance of the model quality. The next one is the non-stationarity. We are dealing with climate change, of some human interventions that change the catchment. So if you train your data and you are aware that after that some changes has happened to the data, to the catchment, perhaps you may need to revisit your calibration. So don't leave it because some new data may change the story totally. And the aggregation of performance metrics. Don't rely on one metrics. Always use multiple metrics in order to see the full picture of the model performance. Okay, I think that's all. What's next? I think I see also in the chat box there are some requests for the trainings. That's exactly what I want to highlight. The next slide, I want to say that today's idea was basically for giving a bit of general introduction to the topic, to the ML application in rainfall-runoff modeling. But if you are interested to know more, perhaps, Tarquin, maybe you go to the next slide that shows some of the things that you may be interested, like, for example, more advanced algorithms like LSTM or DNN algorithms or neurofuzzy. We will be happy to perhaps think of it, because we have some plans to run some hands-on trainings for this type of advanced versions that will include programming as well. Means that we will help you guys to do some level of programming to achieve development of those models for forecasting, for hybrid models, and also the challenges like data preparation, input selection, model optimization, and of course, interpretation. So all these things are upcoming, and when the details are ready, of course, I will inform you about it. Okay, and I think we are now ready to move to the Q&A session, if I'm not wrong. Anything else in the slide? I think no, QA. So let's start with whatever is available here. I start with a couple of questions that I saw here. Yep.
I see one that is asked by Sarah.
Yep.
The question is, given the daily data resolution, how do ML models like XGBoost compare to RNN like LSTM or GRU in capturing long-term catchment memory and base flow decay? So the problem of the difference between XGBoost and RNN like LSTM is that the data load that you require for LSTM is far greater. When we're working with daily data resolution, the model can only work well if there is sufficient years of data, much more than what XGBoost would usually be comfortable with. And provided that there is sufficient data, without it, the modeling performance of LSTM can underperform compared to XGBoost, especially when we're talking about long-term memory, right? So provided that the long-term memory can encapsulate a lot of events, infrequent events, like if it only has 3 flooding events, LSTM is unlikely to capture enough of those associations. You have to present it multiple more, and so typically you have to rely on a much longer data set for it to become at least comparable to XGBoost. So that's the pros and cons of these two models. They both can perform quite well. It just depends on how complex the data is and how long of data do we have.
That's right. And also I add to that from hydrological point of view, generally, I'm in favor of using more data, because we know that the longer the data set is, means that you have more information about past events. And even in the traditional hydrological modeling, we do that, because if you look into the longer data set, the chance of understanding the catchment better and having like a nice diverse range of past events in your calibration process is higher. And because of it, definitely LSTM working with very long hydrological time series is getting some results that are closer to what we expect from, for example, a good hydrological model, the traditional hydrological model. I see another question or request about trainings about training on LSTM. Definitely, that's one of the things that we have in mind, but of course the details of it will come up later. So I will update you whenever I get that information ready about it. Anything else? Let me see if I have anyone else has any question? We have time, around 10 minutes. If anyone has any questions, please feel free to put it in the chat box and we cover that. And by the way, I also need to add one thing that I mentioned earlier. The session will be recorded, is recorded actually, and is going to be uploaded in the channel. Those who have registered, we will send the material to them perhaps soon, in 1 or 2 days. And we will definitely keep you updated if we have some sort of hands-on trainings planned, so you can be aware of it. And if you're interested, you can register for that. Okay. Any questions? And by the way, if you liked this webinar, you enjoyed it and you found it useful, please consider subscribing to the channel to be aware of what we are uploading there, the videos, and also the webinars that we are going to have. Feel free to share it with your friends and colleagues, and stay in touch because more to come. Yeah, there are a lot of things we have in mind to cover on hydrological and hydraulic modeling, not only on ML, also the traditional ones. So yeah, be aware of that. Stay tuned and we will update you. Thank you very much. So I think if we don't have any questions, perhaps we can close the session at this point. And I would like to thank you, Takwin. Thanks for your help running this session. It was very helpful. And as usual, very great to work with you. And hopefully that continues in the future.
Likewise.
Thank you very much, everyone. Thank you.
Right.
Any
Thank
final
you,
note,
everyone, for
Takwin?
attending.
Thanks.
Have a nice day wherever you are.
Yeah, and I also add that based on what I checked, actually, we had representatives from all continents this webinar. Based on the registration, we had representative from North America, Europe, Africa, different parts of Asia, and of course, Australia. I have one question. What is that? Can we have the training material presentation? Yes, I think I mentioned that. Maybe I put the link again here. So you can just click on the link, add your email address there, and we will provide it. Yeah, definitely. Okay, good. Have a good day or night, and see you in the next one. Thank you very much.
Right. See
Goodbye.
you. Bye-bye.
See you. Bye.